Welcome to our poster session titled Village Game Using Reinforcement Learning. Our team is Meghala Anand Kumar from New York City, Rakesh Talanki from Atlanta, Georgia, Bowden Jr. from Curitiba, Brazil. What is the problem we are trying to solve? Is to convert a popular board game called Village Game into an AI problem. What is the objective of the game? To build an agent using reinforcement learning techniques to maximize the earnings by finding an optimal policy and coming close to human achievable solution, which is also called as Oracle solution. What is the game about? Here the farmer has to make decisions to plant corn, bean, cotton, harvest a crop and sell the crop in the marketplace. The money earned by the farmer depends on market conditions. During the game, the farmer can also decide to buy cows, and the milk produced from the cows can be sold and can earn more money. There's an expense the farmer has to make, which is to maintain his family. The objective of the game is to find out how much is the maximum value the farmer can make at the end of the game. At any point in the game, if the farmer doesn't have any money during the game, then the farmer has lost the game. What is our motivation for us to pick this problem? One is we feel once this game is produced and children start to play, it can have us huge social implications. They learn to make decisions, learn and understand about farming, and at the same time, understand the responsibility of maintaining a family. What is the other motivation? This problem gives us a perfect opportunity for us to apply the techniques learned in reinforcement learning techniques in the class and apply for this problem. Let us get into details of the game. In the picture, the one marked in green is in the scope of the game and the one marked in blue is out of the scope of the game. In our game, the farmer starts at $225, has 100 labor units, has 13 weeks, each episode is a week, and goes with only one crop, which is corn. The weekly cost to manage the family is $25. For each episode, the farmer can either win, lose, or continue to play the game. There are certain states in the game and certain actions the farmer can take, and the value of the corn can vary depending on the probabilistic nature of that episode. This is where the stochastic nature of the game comes into picture, and different algorithms will perform differently. Our implementation is based on Python 3, OpenAI Gym, Jupyter Notebook, and TensorFlow. We have approached the problem using three different solutions: Q-learning, function approximation, and deep Q network. Let me pass it on to Bowden, who's going to talk about Q-learning and function approximation.
Thank you, Rakesh. I will present our initial attempt to solve the problem as a MVP. We model using OpenAI Gym, then we learned the best solution using reinforcement learning. Finally, we tested the solution, making the agent play the game. Since transitions and rewards were unknown, we used model-free solutions: Q-learning, function approximation with states and actions, and function approximation using other features. The Q-learning process interpolates the predicted Q value and the new one. We are also showing the implemented Python code. Along with Q-learning algorithm, we used epsilon greedy algorithm, exploring in the beginning and exploiting towards the end with dynamic values of epsilon. When the agent plays the game, the expected value after 1,000 episodes is around 185. Using the same model, we can try a different algorithm to solve the problem: function approximation using state action pairs as features. When the agent plays the game, the expected value after 1,000 episodes is around 150. If we compare Q-learning with function approximation, we can observe that in Q-learning, the agent learns values for states, and in function approximation, the agent learns values for weights of action and states features. If we take a look at the first week state, we observe that the best value of weight suggests the best action, and it makes sense to plant at the beginning of the game. To conclude, we can obtain better results using manual defined features. After learning with this new set of features, we obtain an expected value of approximately 175. Now I will pass on to Megala.
Thank you, Gordon. We have developed three different deep Q-learning models to approximate the Q-value function. In the first model, the input layer represents all the combinations of states and actions, and the output layer represents all the actions. And there are three hidden layers. The objective of this network is to minimize the mean square error, that is the error between the target and the prediction. Here the target is defined as the reward if the state is the terminal state. Otherwise, it is the reward plus the discounted Qmax value. DKN1 uses Adam optimizer to learn its weight, and this network takes several hours to learn as the input layer has a very large number of neurons. To overcome these difficulties, we have developed DKN2 where the input layer represents only the states and the output layer represents only the actions. This network learns very quickly within a minute and produces good result. Here we used stochastic gradient optimizer with momentum function to accelerate the learning process. And we know that DQN models are not constrained by the definition of the Q table. So we have developed DQN3 to play the game for three crops. This DQN3 is exactly same as the DQN2 and learns its weights very quickly and produces good results. Thank you. I hand over this presentation to Rakesh.
Let's compare the results of different algorithms in these graphs. In the learning graph, as you can notice, in the green graph, Q-learning performed really well, whereas the function approximation didn't perform that well in learning. To our surprise, function approximation really performed well, as good as Q-learning in the playing conditions. Let's compare the results to the Oracle solution, which is $225 here. Q-learning performed best at $184 with small number of states, but the model is not scalable once we start adding more crops and actions. Function approximation with state and action, it performed at $151 reasonably well, but training is unstable. We need to add features to make training more stable. Once we added custom features, the algorithm performed better at $174, and this training was also stable. Right? Let's compare to DQN. In a state-based action model, DQN performed well at $152, but the number of states is too big because the money and the labor units are part of the model, and hence the training becomes very slow. So once we started to use function approximation, state-based one-crop model, the performance was poor at $112, mainly because the features that we picked. So there's a manual labor involved to pick the right features. We also tried the model with 3 crops, and the model performed really well. So what is our recommendation going forward? We recommend to use DQN with function approximation as this gives good performance and can manage states better than the other models we have used here. Hope you enjoyed our presentation. Thank you all from Meghala, Rakesh and Boden.